So today we will look at graph theory. Graph theory and also some of its application. Okay, you can just call me Prof. Niza. Just simple, Niza. Okay, what is actually a graph? Okay, so the first definition is graph. So we normally use graph, the symbol as G or gamma. G or gamma. Okay. Now, normally with a graph, for a graph, we have a set of vertices, which is we call V, vertices, and we have the set of we call edges or E. And some equal, okay. And some authors, they put F as a function that connect two vertices with one edges. So vertices in Indonesia, what do you call vertices? In Malay, we call mercu or bucu. And edges, or we call pinggir or sisi. I'm not sure in Indonesia. Okay, so let's draw a graph. Okay, so this is a graph. How many vertices?
Six.
You can put in the chat, but I cannot really.
Six.
Six. Somebody has to turn on the sound. We have 6. So maybe we call it a graph G. So we have 6 vertices and how many edges?
7.
A, B, C, D, E, F. A, B, C, D, E, F. 1, 2, 3, 4, 5, 6. Somebody said 7?
6. Sorry. Yes.
Okay, if you have this F is not this F, yeah? Sorry, it's a little bit confusing. This is called a loop, where you go from the same vertex to itself. So this is called a loop. Sometimes, let me change the notation, because there is F there. Okay. And sometimes we write the function, this F, as I think this is how we write for the edges, in which for the function of an edge is to put the vertices together. So for A, there's 1 and 2. Okay, so you can write F. You can now write F for each edge. Okay, so you have FB, FB will be 1 and 3. This is called undirected graph. If you have an arrow, then it's called directed graph. Okay, so you can put FB as 1, 3, which is actually 3, 1. Okay, I cannot really see the chat because it's quite far, my camera, so you can just turn on the mic and you can ask question or you can say something, yeah? Okay. For or you call titik or now next is what is the degree of a vertex? Degree of a vertex. The degree of a vertex is how many edges at that vertex. How many edges? Okay. The number of edges at that vertex. Okay, so everyone, you can write what is the degree of each vertex in this graph. You have the degree of 1 equal 1, 2. Degree of 2 equal 1. What if I have one vertex like this? This is called isolated vertex. Isolated vertex means there is no edge. There is no edge. And the degree is 0. 0. For here, the degree is 0. So the degree of 3 is 3. The degree of 4 is
2.
Right? Here, here, and here. The degree of 5 is 2. The degree of 6 is 1. Okay, so this is the degree. Now, next definition is adjacent vertex. Adjacent vertex. If you have an edge in between two vertices, they are called adjacent vertex. Like 1 and 2, that's an edge. So 1 and 2 are adjacent. 3 is adjacent to 1, 6, and 5. 2 and 3 are not adjacent. 3 and 4 are not adjacent. So that is adjacent. I mentioned about a loop. Loop is an edge from the same vertex. That's a loop. This is isolated vertex. The degree is 0. Okay. Now, next is a path. What is a path? Okay, a path in a graph consists of a sequence of vertices and edges. Okay, now we will write a path for some distance from one vertex to another. For example, okay, let's say I want a path of distance 2 from 1 to 5. A path of distance 2 from 1 to 5. So there will be 1, B, 3, D, 5. So the distance is 2 because we have from 1 to 5, 1, 2. You can also have from 1 to 6, BC, that's a distance of 2. What if the question is, give me a path that has a distance of 5. Give me a path that have a distance of 5. I will start, for example, two, A, 1, B, 3, D, 5, 1, 2, 3, E, 4, H. What is it? I heard someone talking. Can you see it? Yeah. 5, yeah? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So that is a path of distance 5. You can go back if you want more. 5, 6, 7, 8, 9, and you can go back and forth. This is undirected graph. If you have directed graph like this, you can go only this way, not this way. Okay? So you can also have directed or undirected. Directed or undirected graph. Okay. Now, next is connected graph. A graph is called connected if there is a path from each of the vertices. If there is a path from one vertex to another. Okay, so without J, this graph is connected. With J, this graph is disconnected. Okay, so without J, this graph is connected because every vertex is adjacent to another. There is a path. Okay, since there is no path from this graph to J, so together with J, this graph is disconnected. So connected graph and disconnected graph. Versus okay. Now we also have a simple path. A path is called simple if in the sequence there is no vertex appear more than once. Okay, a path is simple if no vertex appear more than once. Just now, I already erased. But an example of simple path is if you go like this is simple. If you go like this is simple. But if you go 2, 1, 3, 6, 3 again, that's not simple. Because there is a 3. If you go 1, 3, 5, simple. 1, 3, 5, 3, not simple. So there is a difference between a simple path and not a simple path. If you have a graph which is disconnected, like this is called the component of the graph. This is one component, this is another component. Sometimes you have a graph like this. This is one whole graph, okay, in which you have this is called a disconnected graph with seven vertices, 7 edges, okay, and 2 components. Okay, this is how we call components.
Kemudian
Okay. Now the next one is what we call a discrete graph. Discrete graph. So if we have a graph with n vertices and no edges, we call it Dn. If you're taking also group theory or you study group, we also use D sub n, which we call dihedral. But here, when I call D sub n in graph, this is called a graph, a discrete graph with n vertices and no edges. How do you draw D1? How do you draw D2? And how do you draw D3? Easy, right? Indonesia say easy is what? Gampang. Gampang. D2. D3. Okay, very easy, yeah? Gampang. Discrete graph. Next, I introduce complete graph. Okay. Let me, I can just erase this now. Okay, complete graph. Okay, a graph is complete. Okay, I have Kn. Okay, this is very common or standard that we use Kn to denote complete graph on n vertices. Complete graph on n vertices. So you have, for example, K1, and the definition is that every vertices are adjacent. Every vertices are adjacent. So K1 is just 1. K2, you have 2, which is adjacent. K3. Why do I draw like this and not that? Because I want to show they are all adjacent. What about K4? You have 4 vertices and draw edges, so they are all adjacent. has to be adjacent to all, the same as this. So this is K4. Then you can draw K5. 1, 2, 3, 4, 5. Right? Then how many edges for Kn? How many? I have a student here also, one with me. Now, first we know the degree. The degree is always n minus 1. Any formula for the vertices of a complete graph? You see, the degree here is 0, the degree here is 1, the degree here is 2, 3, and 4. But that is the degree. What about the number of edges? Can you decide what is the number of edges for Kn? For all n. You see, this one, 1, 2, 3, 4, 5, 6. Okay. This is 3. That's the formula. Now it's easy, right? You can try and Google. Anyone has any answer? The number of edges. It's a formula. I'm not going to tell you. Okay. All right. Next graph is called a line graph. A line graph, or sometimes mostly known as a linear. This is most common. Okay, linear graph. Now, this linear graph has what when we say n vertices, and there is an edge from that 1 until the n. So we draw like this. L1, just 1. L2, just 2. L3, and so on. So these are all line graphs. Okay. We start, okay, I still have 35 minutes. Now, the most one of the most famous path is called Euler path. Okay, how do you say Euler path? A path is called an Euler path if in the graph and the path includes every edge exactly once. Okay, the path in the graph is called an Euler path if it includes every edge exactly once. And I didn't mention this yet, right? A circuit is a path A circuit is a path that starts and ends at the same vertex. Okay, let's look at two examples. Yeah. This is like an arrow, yeah? Just call 1, 2, 3, 4, 5. Okay? A, B, C, D, E. Okay? 1, 2, 3, 4, 5. 5 vertices. So we write, suppose this is a graph G. Vertices of G is 1, 2, 3, 4, 5. And the edges A, B, C, D, E. Now you can write the degree of each vertex. 1 has degree 1, 2 has degree 2, 3 has degree 3, 4 has degree 2, 5 has degree 2. Okay, that's the degree. This graph is simple, there is no loop. This graph is connected because every vertices are connected or adjacent. Now we want to find an Euler path. Can somebody give me an Euler path? We want to have a path in which every edge is included exactly once. Can you find it? Okay, let's start with here. You see? I draw like this, yeah? Right? So I start from 1, A3, B2, C5, D4, E3. So I start from here. I include every edge. I didn't say vertices. Every edge exactly once. So this is an Euler path. Okay. Okay. So let me write. Without the edges, yeah? I can write like this. 1, 3, 2, 5, 4, 3. Some authors, they don't put the edges, but it's actually better to put in the edges so you can see exactly 1, A, 3, B, 2, C, 5, D, 4, A, 3. So you see A, B, C, D, E. You can really see the edges. They appear only once in the path. So there are two ways. You can also start from here. If I draw like this, right? I can also get the Euler path. So there are two ways. I can start from 3. Right? So I can have 3, B, 2, C, 5, D, 4, E, 3, A, 1. So you have B, C, D, E, A. Also, an Euler path. So you can start by more than one ways. Okay, now you cannot have Euler circle. There is no way you can start and end at the same vertex without going through the edges more than once. If you want to go back, you start from here. If you want to go back to here, you have to go another one. This is not anymore Euler. If you start here, then you want to go, you have to stop here. You cannot go back. So there is no way. What about you start from here? If you stop there, you don't have Euler path, right? You didn't go. So you have to go back up, which is a different vertex. So this is just an Euler path, not a circle. None. It's none here. Okay, I have to draw another one. So let's draw this. Yeah. 1, 2, 3, 4, 5. Okay, so try to draw an Euler path. An Euler circuit is an Euler path. Okay, but an Euler path might not be Euler circuit. Okay, so you go 1, 2, 3, 5, 4, 3, 1. So that is an Euler circuit. 1, 2, 3, 5, 4, 3, 1. You can start from anyone. You can start also from 2, right? Go back to 2. You can start from 4. You can go this way, or you can go this way. So there are many ways to get an Euler circuit from this example. Many ways. You can start from here, go here. You can start from here, go here, and many ways. Okay. There are some properties to get or to decide whether in a graph there's an Euler path or Euler circuit. Okay. One thing is, if every vertex has odd degree, no Euler circuit. Just now, my example didn't give one for this one. If in a graph, every degree has even degree, every vertex has even degree, like this one, the degree is 2, the degree is 2, the degree is 4, the degree is 2, the degree is 2. If every vertex in a graph has even degree, then there is an Euler circle. Okay, so that is a proof for that one, but I'm not going to give you. Just a bit of a homework for everyone. I want you to Google this after and read this story. The 7 bridges of Königsberg. This is a very, very interesting and famous problem. Okay, I think this is in Germany. It's called the 7 bridges of Königsberg. Or is it in Soviet Union? Russia or Germany? Try to Google. Yeah, I think it's in Germany. There is a river. There's a river that goes through the city, and there is bridges, and there are 7 bridges. Okay, and the people want to see if they can go to every bridge exactly once. So from this real situation, you can make it like a graph, and then you can solve it mathematically. This is what we call as mathematical modeling. Okay. So read through about this story, but I will draw the more or less. This one more. Somewhere like this. No, not this one. I think this one somewhere here. No, not this is the way in. Okay. So this is like graph. Can you go like here, then go this bridge, then go this bridge? If you try and look at it as a graph, you can see that we are trying to go through the edges exactly once. So from there, this is model, and we got a graph like this. Okay, that is the graph. So the people are wonder whether you can walk through the city and you can cross the bridge exactly once only. Okay. 1, 2, 3, 4, 5, 6, 7. So like this one, you go, you stop there, right? You don't get this one. Okay. So the answer is, it's not possible. It is not possible. So the problem in the real life, you don't have to go through the bridge, go back and forth in the island. There's one island in here, the city. You can just model through graph, and by the property, you can show this is not possible. Okay. Related to the Euler, another important and interesting property is the Hamiltonian path. Hamiltonian path and also circle. Okay, if for Euler it's the edges, for Hamiltonian is the vertices. Okay, so a Hamiltonian path, a path that contains every vertex exactly once. A path that contains every vertex exactly once. So for the circle, you start and end at the same vertex, right? So the first and the last one is the one that appears twice because it's a circuit, but the rest is just once. Okay, let's try this one. 1, 2, 3, 4, 5. One, two, three, 4, 5. So we cover all vertex once. You can go 5, 4, 3, 1, 2. In any way, as long as you have the edges. What about this? Oh, the same. Okay, let me give you one example. This one. Give me one Hamiltonian path. 1, 2, 4, 3. Or 1, 2, 3, 4. Right? This can also be a circuit. We can go 1, 2, 3, 4, 1. So it's a circuit. All right. Okay, I need to move on to some examples or in the real life application. I have 10 more minutes, right? Okay. But before that, there are some other graphs that is important. If any of you are interested to continue your degree S1 or S2 or S3, research are done on the bipartite graph and also multipartite graph. You can partition the vertices into different sets. For example, for 2, and then if we add complete here, that means bipartite you have 2, 3. Okay, within this set and this subset, they are not adjacent, but they are adjacent like this. And like this. So this is called complete bipartite. If you have another one, maybe you have another 3, 3, then another one, it becomes complicated. So this is another thing that we have for graph. And then by the graph, you can define many other properties, which include, I don't have time to include all, but I just write down some. Independent number, chromatic number, domination number. This is some of the properties of the graph. Okay. Let me ask my student here, Zali, if you can share. I want to share the application of graph in slides. Yeah. Are you able to share screen? Cannot.
Okay.
Maybe you can raise your hand so they can make you co-host. Your name is Ghazali, right, in the Zoom? Can you make Ghazali co-host? Ghazali bin Ismail or Ismail? Still? Okay, you raise your hand already. Can the host make Ghazali co-host so he can help me share? Otherwise, you can just help me. Zali, you can just help me go next, yeah? I will share. I will share, it's okay. Okay. It's okay. Okay. Okay, so next. Okay. Okay, since you are not here, I share you the map. I hope you can all come to Malaysia and also to UTM, maybe one day to visit us. All right. So you know where you are over there, down there, right? That's the green one is the Malaysia. All right. So you see, we are just near Singapore. There are two campuses of UTM, one in Kuala Lumpur and one in Johor. Okay, so to show you closer, that's Malaysia. So UTM Kuala Lumpur is over there in the central of Malaysia, and Johor Bahru is, you see on the right, is just near Singapore. So you can also fly to Singapore and take a bus or train. All right. Now, mentioned by the MC earlier, this is my background. Okay, I received my bachelor, master, and PhD from this university. Okay. Okay, graph theory has quite a number of applications in computer science, computer network, electrical engineering, math, of course in math, physics, chemistry, biology, social science, linguistic, and also what we do every day, Google Maps or Waze, right? Okay. Okay, this is Kuala Lumpur LRT. If you go to KL, I think some of you have been to KL, right? So you can see the LRT. So all the road of the train, okay, the train station is the vertices, and the road is the edges. You want to go from one to one another, so you have to find a train, right? So you have to find a train that has the road. Otherwise, you cannot go from one to another. Sometimes you have to go and change the train. Okay, this is actually modeled in graph theory. Now, if you have taken Malaysia Airlines or you have Malindo, right? They have their own flight route. So this is from Johor. You can see I didn't have one to Indonesia, but within Malaysia, you have this path. So there is no direct flight from Johor, for example, to Kuantan, Pahang, or to Terengganu, or to Kota Baru. So the distance is not one, the distance is two. Okay, okay, next. In computer science, if you are interested in doing more research or taking classes from computer science, you can see, you will see graph in the modeling, analysis, in web document, optimization, web page. They use all this, and image analysis. In computer networks, we have internet, there's a router. You have to have connection, right, in between the router and the switch to all the PC. Like my laptop now is using the Wi-Fi from the internet. So you also have a lab, computer lab. So it needs all of this connection. So our devices are the vertices, and the connection from internet or Wi-Fi or the cable is the edges. Now in electrical engineering, they have electrical circuit in which they have this network, and you can see the graph. So sometimes the circuit can go only one way. So in that case, they have to use the directed graph. If you have a map, you have to have a plan, and you have to optimize the way. You don't want to go round and around, right? So the one on the left is before they do optimization, and the one on the right is after. So that is the shortest path. And how do you go from one place to another? The shortest way. You know, if you use Waze, Waze normally will send you to go at the back of people's house, right? Because they want to go faster. Okay. And another, I think Google Map, the one that go a shorter distance. Okay. Human brain. This is very interesting because I have seen some research doing human brain networks. Some use topology, some use the graph, some use fuzzy, and some use also graph theory. Okay, so the real thing is the brain, and inside the brain, as you know, you take biology, right? There's so much network inside our brain. So the connectivity between all the points in the brain can be look like a graph, right? That's all the connection is the edges. You can see data pre-processing, they are done, and how do you go to the even metrics, they translate into this. And many work is done or research done to look at the epilepsy of people, Sawan, right? Penyakit Sawan, that is also can be modeled by mathematics. Okay, next. Okay, this is ongoing research by my student in which he's working on doing mathematical modeling on DNA strings. You know, each one of us has DNA of our own, consisting of the A, C, G, and T. So it's a long string. From this long string, we have what we call a system or splicing system. This long string, we can cut at a certain place and we can recombine. So we call it a recombination DNA. And from this string, we can make it as a graph, and we call it a graph splicing. What we cut is using the enzyme. This is the real thing in biology. They pick the enzyme from plants, from animals, and this enzyme can be put in the DNA and it cut at specific places. Just press once. Okay, and so this string, I write it as graph because DNA is they come in pairs, A with T, C with G. So you have the one together, connected in a bond as the edges. And then the eco R1 you see on the right is the enzyme, where the dot dot is where it cut. Okay. So when it cut, next. Oh, sorry, that's it. When it cut, it separate and recombine. Okay, I am sure, if not 100%, most of you have social network, right? You have Facebook, you have LinkedIn, you have YouTube, you have Instagram. There are actually a path in between most of this, not all. Like if like this morning, I put up a story in Instagram, I make it to do the same for Facebook. So Instagram has a path, direct path to Facebook. So the distance is 1. If you change your profile photo, right, in Instagram, you can do it automatically change in the Facebook. So this kind of thing is what we can also model in graph. Okay. Also, the architects, when they do the floor plan or building plan, they can plan and make it also model as graph. Like you have a master bedroom, how do you go, like in a museum, I think it's normal. How do you go through a museum just one way? Last month, I went to Surabaya and we went to a museum there. So go in this way and then go to each and every room, make sure, and go out another way. So they are actually doing if they have the same door, that will be a circuit, right? But go to every edge or point or vertices once. They don't want you to go back and forth. If they have a different entry and exit, that is just a path. It's not a circuit. I also went inside the submarine in Surabaya. Yeah, IKEA also, right? So the submarine, you go this way, and then the museum, same door. So it's a circuit. The submarine, you go this way, you go, the submarine is just long, right? And you just go straight. Then you go exit. All right, next. People doing linguistic. Okay, it's not my area, so I cannot explain in detail, but they also have this connection in between. They call it a Greek etymon, Greek derivative, Latin derivative, model, representation, diagram, all these things. Linguistic people also, maybe they don't know that they're using this as graph, in graph theory, because this is modeling in mathematics. Okay. Okay, I think that's about it. The sharing from me.